Okay, so let's look at some free fall problems where the object is being thrown or launched vertically up into the air. So here a tennis ball is thrown, that's a keyword, vertically upward with an initial velocity. We know that once the tennis ball leaves the person's hand, it is freely falling because the only force acting on it is gravity, assuming negligible air resistance. Therefore, it's going to be uniformly accelerating. Okay, also here a key word is that it's got an initial velocity. That's positive 8.0 meters per second. It says what will be the ball's speed when it returns to its starting point, and then how long will the ball take to reach its starting point. So if we draw a picture, here's our tennis ball. It's going to be thrown up into the air with an initial vertical velocity of positive 8.0 meters per second. Now, this y just means that now we're not in the horizontal dimension anymore. We are now in the vertical dimension. It's going to hit like a peak location, and then it's going to come back down to that same starting position. We know that when it travels upward, it's going to not speed up. When it travels upward, it's going to slow down. And then when it travels back downward, it is going to speed back up. Okay? So here it says what will be the ball speed when it returns to the starting position? Pretty simple. Here, what is the final vertical velocity? Well, it is negative 8 meters per second. This is symmetrical. Okay, we talked about this in the previous video. So when it's asking for speed, though, you can just write 8.0 meters per second. Speed is a scalar quantity. You do not have to include direction there. Okay. Another little tidbit of information, the velocity at the peak, remember, is instantaneously zero. Then it says how long will the ball take to reach its starting position. So the ball here is going to go up, hit the peak, come to a stop, and then come back down. And we want to know this entire time. We already have some information. We know the initial vertical velocity. We know the final vertical velocity when it comes back to the same position. And we're looking for the time. And we know one more thing that's not specifically told to us, but it's true for this type of problem. And that's the acceleration due to that gravitational force near the surface of the Earth. And that's negative 9.8 meters per second squared. That right there is enough information to solve for time. We also know that the initial position, we can just say it's 0, and the final position is 0 because it's going to start and stop at the same location. So if we want to find time, I'm just going to use the easy equation here. So the easy equation, we have VYF. On the equation sheet, this is an X, and that just means horizontal. Now we're looking in the vertical. So VYF equals VY naught plus, instead of A, we're dealing with G, the acceleration due to gravity, times T. Now I'm going to solve for T. So I'm going to subtract VY naught by both sides. So this is VYF minus VY naught equals G times T. And then I'm going to divide both sides by G. So the time is VYF minus VY naught divided by G. So now I can just plug in numbers. Now when I plug in my numbers here, the time is going to be VYF is the negative 8 meters per second minus VY naught, which is positive 8 meters per second, divided by negative 9.8 meters per second squared. Now when I do this, I get the time is negative 16.0 meters per second. That would be the change in velocity here, divided by negative 9.8 meters per second squared. So if I plug that into my calculator, notice the negatives will cancel. You can't have a negative time. So 16 divided by negative 9.8, and I get 1, or just 16 times divided by 9.8, 1.63 seconds. Now here's the thing with sig figs. The g is a constant. The acceleration due to gravity is constant. We don't look at it in terms of sig figs. And up here, I subtracted -8 minus a +8. And so we have to look at place values. Since I have a 0 here in the tenths place, and a 0 here in the tenths place, this 0 in the tenths place is significant, so that gives me 3 sig figs. So my answer should have 3 sig figs. Now there is another way to approach this problem. We could find the time from here to here. Okay? If we do that, the way it changes the problem, instead of the final vertical velocity being -8, the final vertical velocity is 0. The initial vertical velocity is +8 meters per second, and then we divide by g. That's going to give us, though, half time. Okay, that's going to give us half time. So then we could just double it to find this whole time. So that's another way you could approach the problem. The last thing I want to look at is units. Notice we're taking meters per second divided by meters per second squared. If I flip and multiply, notice the meters cancels. One of the seconds cancels, and so my units, I'm left with seconds, which makes sense for time. Okay. Now I want to look at a slightly more difficult problem. Okay, so Stephanie here hits, that's a key word, a volleyball from a height of 0.8 meters and then gives it an initial velocity of positive 7.5 meters per second straight up. Okay, so here is Stephanie. Here's the ground. Here is Stephanie. She's like bumping this volleyball. We'll give her some hair. Here's the volleyball. The volleyball is going to go straight up, and then it's actually going to come back down and hit the ground. There's the volleyball. Okay. How high will the volleyball travel relative to the initial position? Now, I will say, if we say that the ground is y equals 0, we can do that. Notice here the volleyball is starting at y equals 0.80 meters. Okay, that's the start position. If we say the ground is 0, okay, we know the initial vertical velocity is positive 7.5 meters per second. We know that after she bumps it, it's going to accelerate due to gravity, and that near the surface of the earth is negative 9.8 meters per second squared. We want to know like this final position, okay? We want to know, now if we find this final position, that's going to be relative to the ground, and we really want it relative to the initial position, but we can deal with that later. So we want to know the final position. Now there's one more thing that we know that maybe is not specifically told to us, and that's the velocity. So we're only looking at like from here to here because we want to know the height. And we know the velocity, and we'll just call that VYF, at the peak is 0. So we're only looking at the motion from when it leaves her arms to the max height. How high will the volleyball travel? So we have enough information here. Notice I don't know anything about time, so I'm going to use that uniform acceleration equation that does not include time. So that's going to be y equals, nope, I lied. That's going to be Vy final squared equals Vy initial squared plus 2G times Y final minus Y initial. Okay, so I'm going to rearrange this equation to solve for this Y final. First thing I'm going to do is subtract the Vy naught squared from both sides. So Vyf squared minus Vy naught squared. Then I'm going to divide both sides by 2G. Divide by 2G, so 2G. And then I'm going to add over the Y naught. And that should give me the final position. So if I plug that into my calculator, that's going to be 0, because that's the final velocity at the peak, minus a positive 7.5 meters per second squared, divided by 2 times negative 9.8 meters per second squared, plus 0.80 meters. And now this is going to give me the position relative to the ground. And we'll go back later. So 0 minus 7.5 squared divided by 2 times negative 9.8 plus 0.8. This is 3 point, sig figs, let's see. Let's just go with 3.7 meters. Now that's from the ground. If we want to know from the initial position, we actually need to subtract that 0.8 out. So that's going to be, let's say, 2.9 meters here. That's how high from the start position. And then the 3.7 is how high from the ground. Now it says how long will it take the ball to hit the ground. So if the ball goes up and then comes all the way back down to the ground, notice that it's landing lower than where it started. So this is a little bit more difficult. Okay, I'm going to actually erase this because things have changed. Now the final velocity is not 0, okay? Because we're going to go all the way from the start to where it hits the ground. So the final vertical velocity is going to be something bigger in magnitude than the 7.5 meters per second, okay? So we still know the initial position. We can say now that the final position is 0. We're looking for time. Now this is what I would do. You could use the quadratic formula to solve for time, okay? Instead, I'm going to separate into two problems. I'm going to first find the final vertical velocity, and then from there, solve for time. So if I first find the final vertical velocity, I'm going to use, we don't know time, so I'm going to use the same equation. Vyf squared equals Vy naught squared plus 2G, and this would be delta y, which delta y would be negative 7.5, nope, not negative 7.5, negative 0.8, negative 0.80 meters, because this is y final minus y initial. So that would be 0 minus 0.8, okay? So I'm going to solve for this final vertical velocity, which is going to be the square root of Vy naught squared plus 2G times delta y. So if I plug in my information, I'm going to have 7.5 squared plus 2 times negative 9.8 times negative 0.8, and then I've got to take the square root of that. So notice the velocity here is negative 8.5. It's actually negative point or negative 8.481, whatever. Negative 8.5 meters per second. It's negative because the ball is traveling downward. And notice that the magnitude, so like if the ball were to come back to the same start position, its velocity here would be negative 0.7 or negative 7.5 meters per second, but because it's traveling further down, it speeds up even more. Okay, so we got that. So now we can use this equation to solve for the time. So the time is the final vertical velocity minus the initial vertical velocity divided by g. And so this would be negative 8.5 meters per second minus a positive 7.5 meters per second divided by 9.8 meters per second squared. So if you plug that into your calculator, we get 1.63 seconds. If you have any questions, go see your teacher.